The meeting is being live streamed. Go ahead. Okay. Da mi recimo možemo pauzirati stream i samo pokrenuti. The meeting is being live streamed. Go ahead. Okay. Da mi recimo možemo pauzirati stream i samo pokrenuti. The meeting is being live streamed. Go ahead. Okay. Stream i samo pokrenuti. The meeting is being live streamed. Go ahead. Okay. Ok, ajde ti molim te kreni pričati, ja ću samo izaći svojim laptopom van da vidim da li te normalno čuje. Pa samo da istestiramo. Ti slobodno kreni pričati.
Test 1, 2, 3. 1, 2, 3, test.
Ok, ajde ti molim te kreni pričati, ja ću samo izaći svojim laptopom van da vidim da li te normalno čuje. Pa samo da istestiramo. Ti slobodno kreni pričati.
Jedan, dva, tri, 1, 2, 3, test 1, 2, 3. Ja, 2, 3. Okreni. Pitanje je, čuju naši gledatelji šta?
Ne može li
čuo išta?
Pa čuje se, okej.
Ok, super. U čemu je trik još, kad se ovaj prozor otvorio, na njemu isto trebalo mutati YouTube, zato što on ima još vraća zvuk od njega.
Može, super. Ajmo onda nešto kliknut, ja idem samo Nikoli,
Samo malo da mi pomogne.
mobitel, evo ja ću sad naručiti Nikoli taksi. Evo idemo da mi izrediš za koliko šije.
Eat something, shit.
Thank you.
Shit. Eat something, eat something.
Ja ne mogu gledati.
I need to remind you.
So you can unmute. Okay. Hello, everyone. Welcome back after lunch. I hope you are not going to be too sleepy because we have an excellent speaker now. Shir Kilkish is a member of Scientific Committee of Deve Center for maybe 10 years or something like that. It is a committee made of really top people. Half of them are on the Stanford list of top 2% researchers, including Shir. And but even more important, Shir was a leading author, actually still is, of the 6th assessment report of IPCC. So you will hear today a lecture on what were the priorities and what are the next steps in the climate change science. So Shir, please, the floor is yours.
Thank you very much, Nevin, for this introduction and for the opportunity of giving this lecture at this excellent summer school. So it's my greatest pleasure to share with you this presentation on effective mitigation of climate change, modeling advances, and priorities for AR7. In each assessment cycle, there are coupled model intercomparison projects. So in the 6th assessment cycle, there was CMIP 6. And in the next assessment cycle, AR7, there will be CMIP 7. The ongoing advances in both the side of climate science and the mitigation of climate change are advancing with the modeling and scenario capabilities. But the Earth system is very complex, and there are many feedbacks to take into account in these climate models. The complexity of the Earth system, what will exactly be the feedbacks? How will the carbon sinks, both on the ocean side and the land side, respond to increasing levels of global warming? These are all areas, the tipping points. How do we know exactly how the Earth system will respond? So there are uncertainties. All of these go into the climate models. Then on the mitigation side, we need to ensure that those strategies for mitigation are aligned with these scenarios. So these are the integrated way of looking both on the climate science and the mitigation scenarios that are coupled with those. From AR6, when we look at what were the advances in CMIP 6 over the previous CMIP 5, we see that there are some benchmarking results. This is showing the example from the land benchmarking results, how these two results compared across time. But we still have areas to improve. As I mentioned, tipping points, feedbacks, the complex Earth system, these are all areas that we still need continued advances of our understanding, our scientific understanding, and our ability to be able to model them in an enhanced and advanced way. And permafrost, for example, as permafrost is going at this, providing some amplifying feedbacks for global warming. So there are some advances still to be made on the side of climate science. On the side of mitigation that is aligned with these scenarios, one thing is clear. We need to be acting quickly and more integratively. This is very urgent. And it's clear that unless we halve CO2 emissions by about half by 2030, our ability to reach the critical threshold for those tipping points, 1.5 degrees Celsius tipping points, will be beyond reach. So this is where the urgency of enhancing our modeling capabilities on one hand and showing the effective mitigation of climate change to be able to guide the world, the entire world, to these opportunities are very critical and important. Already, we see that about 24 countries are able to record sustained reductions in CO2 and greenhouse gas emissions in the last decades. And this is very important. Our modeling capabilities need to show how more countries can join this group of countries. And what we see also is that the greatest reductions have been taking place in the energy system, electricity and heat. So when we advance our modeling capabilities, then we can also guide these, the entire world into possibly more sustainable pathways. In the 6th assessment report, we looked into recent developments and current trends, system transformations to limit global warming, linkages with sustainable development, and ways of strengthening our response. And all of this is in the detailed report of the sixth assessment report. Here I will focus on the modeling advances that took place in this assessment cycle. And this is important because, as I said, it is showing us the pathways that we can shift towards the unsustainable energy, land, and resource use into more sustainable pathways. In this third working group on mitigation of climate change, we had a scenario database. About 3,000 scenarios went into this database. These were vetted against criteria, and those remaining, they were run individually through climate emulators. These climate emulators allowed us to look into the temperature outcomes of these scenarios. And according to these results, these were classified into 8 different categories. And you can see the distribution of these scenarios on the right-hand side. Then we as the author team, we also worked into defining storylines for illustrated mitigation pathways. Each of these have different characteristics to show the different mitigation opportunities. Then, based on these storylines, again, the scenarios were vetted, and those scenarios that are illustrative of these pathways were defined. On the side of categorizing these scenarios according to the temperature outcomes, the 8 categories, they start from C1. C1 is limiting global warming to about 1.5 degrees Celsius with no or limited overshoot. Then C2 is limiting global warming to 1.5 degrees Celsius with high overshoot. Then C3 and C4, it is limiting global warming to about 2 degrees Celsius with different probabilities. And then the categories go on. In the part of C1, which is limiting global warming to 1.5 degrees Celsius, we see the scenario SSP1 1.9 that's also used by the first working group, and 3 illustrative mitigation pathways. These 3 illustrative mitigation pathways include renewable energy, low demand, and the third one, shifting pathways. The illustrative mitigation pathways on renewable energy seeks to illustrate the rapid deployment and technology development of renewables, and an important role for electrification. Let's look more into this illustrative mitigation pathway. This is coming from a scenario with about 66% non-biomass renewable energy share in final energy in the year 2050. And the electricity share in final energy is at about 70% worldwide. On the side of primary energy, including biomass, the renewable energy share reached about 84%. So there is still a way to go towards 100% renewable energy systems, and showing that the optimized energy system with 100% renewable energy systems is possible. When we also look into this pathway called the shifting pathways towards sustainable development, this is coupling more the demand reductions also together with the renewable energy, so trying to accelerate the decarbonization process. And as we know, the system transformation requires major shifts in energy, land use, innovation, lifestyle, as well as policy. So this one, shifting pathways, is combining the demand reductions with sustainable development and renewable energy. And it requires more policy tools to remove the barriers, use the enablers to accelerate the progress, and trying to set this direction to guide our efforts, our mitigation efforts. Another advance in AR6 was trying to assess the feasibility of these scenarios multidimensionally. So feasibility is not only one-dimensional, it includes many multiple dimensions, including technology, economic, socio-cultural, institutional, as well as geophysical. So those scenarios in the database, they were analyzed in this multidimensional feasibility aspect. And we see the technological maturity, the mitigation costs, the shifts in demand that are involved in different scenarios, as well as the geophysical aspects. And we see that there are different ways of reaching 1.5 degrees Celsius. Some of these scenarios all pretty much involve more institutional barriers, so the institutional concerns are higher. Economic and technological, they're relatively, they're only waiting for us to use that potential. But in some scenarios, for example, those that might require lifestyle changes, Some of the socio-cultural aspects may require more attention. For example, in addition to the climate crisis, did we also need an energy crisis to get us into reducing more the energy? So these have different ways of being assessed according to feasibility. We need to be able to model 100% renewable energy systems in an optimized way. So this is, we know that this is a priority. In addition to this, we also need ways of increasing ways of modeling the material efficiency. And this has taken place in the summary for policymakers. It is specifically stated that demand management, materials efficiency, and circular material flows, these are generally not considered in recent global assessments due to the relative newness. So this is a new direction to be further pursued in the upcoming assessment reports. We also know from emerging research that there's already some dynamic into looking into material efficiency and global pathways towards 100% renewable energy. So there is emerging research and more can be integrated into the next assessment cycle. Let's take a deeper dive into the AR6 scenario explorer and database and look at how these different scenarios and modeling capabilities are represented some indicator by indicator. Most of the scenarios, they cover very well the energy indicators to a certain extent. But for example, other indicators such as the electrical energy storage or the water withdrawal for electricity, which is very important for the energy-water nexus, or ways of energy services or material recycling, these are less covered by the scenarios in the AR6 scenario explorer. Looking further down into the level of 10 regions, the coverage of these different indicators in database is also varied again. So more coverage for energy indicators, non-biomass renewables, biomass, then less for such aspects as agricultural demand, water withdrawal for electricity, the electrical energy storage, fertilizer use for nitrogen, which is also important for planetary boundaries, land use and forestation, employment, important for co-benefits. And each one of these aspects, if we're able to optimize 100% renewable energy scenarios, these would involve some cross-sectoral synergies. And for example, avoid shift strategies, they require us knowing what is the potential for example, more walkable urban areas or bicycling and walking. And the material recycling aspect, we also need to know more about the circular use of materials. So these are all opportunities. Let's look more now into detail in those scenarios that try to cover this energy-water nexus using the example of water withdrawal for electricity. In some of the regions, there is about a 3.5 times increase, for example, in Africa, for water withdrawal for electricity. But an important question to ask is this within planetary boundaries? Is it within planetary boundaries or not? And across the regions, there are different increases in these different scenarios. So in that no policy scenario, there was that 3.5 times increase for one of the regions. Another important indicator to increase the primary energy from non-biomass renewables, but in different scenarios with different temperature outcomes, the increase is very minor. How can we increase this and also ensure that renewables are integrated in the energy system in an optimal way? Another indicator, which is calculated from the available data, the total renewable energy share in primary energy. Across all of the scenarios, across all of the regions, this reaches about 31%. So we still need more scenarios that have very high renewable energy shares. The maximum with the sample of scenarios come from about a 73% of total renewable energy share in primary energy. It is coming from a scenario with renewables, SSP 1.9, also coupling some of the lifestyle changes. What would it take for us to capture more synergies in these dimensions? So in a cross comparison of, for example, the percentage change in water withdrawal for electricity, which would need to be reduced as a percentage and even come to negative values as conventional thermal power plants are phased out, while increasing on the horizontal axis the percentage change in the renewable energy share in primary energy. So this is a cross comparison. We need to capture more synergies, and the current scenarios in database, these are different data points colored according to the regions. And optimized 100% renewable energy systems will improve these results that will also have beneficial impacts for the planetary boundaries. Another group of indicators, electricity and final energy. Some of the scenarios, for example, it can have about 7.6 times increase from reference year values to 2050, but it varies across the, of course, the scenarios and the regions. Then we can also look at the electricity share in final energy. What is the share of this electricity in the final energy that we're using? The scenarios in this example, about 69%. This is the value in the highest, the maximum value in the scenarios, but across scenarios, these values are differentiating. So how can we ensure that electrification takes place, integrated in energy system in an optimized way, so we know that we can direct in a sustainable manner. Another indicator, the electricity storage. In some of the scenarios, there are drastic increases because it's almost starting from about 0 values. But would all of this electricity storage really be needed if we did an hourly optimization of these scenarios? So this is another question that needs to be addressed. So in this cross comparison, we would need to ensure a reasonable, optimized annual average increase in the storage capacity that's required when we look into the intermittency of the renewables, but at the same time, ensuring that we increase the electricity share in final energy up to 100%. And you will see the data points, they're not at this level yet. So there are additional opportunities beyond these results in both dimensions. Another group of indicators, land use and forestation. It's very promising that there are very high values in some of the scenarios, but not so much in the others. On average, about 11 times increase from the reference year values. Sometimes land use afforestation, which is important for net zero targets for reducing the residual emissions, it can compete with agricultural demand. So looking into the system dynamic, how it actually comes into play. And in some of the regions, the agricultural demand can be coupled with fertilizer use, for here, nitrogen. But is this really required? Can there be a more sustainable way of satisfying the food security for different regions while also minimizing the fertilizer use of nitrogen? So in this cross comparison, we would need to be looking into those scenarios that have percentage change in nitrogen fertilizer use to less and about negative values, a proportional increase in agricultural demand to satisfy the food security. And these are different data points in the existing scenarios shown here. But we would need to optimize in both dimensions in some way for sustainable development. So more sustainable agricultural production and consumption can also be represented here. All of these different scenarios, they have different consequences for global warming. What will be the CO2 emissions, what will be the methane emissions, and all of the other greenhouse gas emissions. So there are, of course, different increases across the scenarios for methane as well, which can also affect net zero year. But when all of these scenarios are run through the climate emulators, for example, in the Norwegian one and the FAIR climate model, we see about 24 of these scenarios, they have an 80% chance of exceeding the probability of 1.5 degrees Celsius. In the MAGIC climate emulator, this value is higher. About 38 of these scenarios shown here have about 80% chance of exceeding the 1.5 degrees Celsius threshold for supporting life support systems of our planet. When we ask ourselves, what can be a sustainable scenario look like? What are the indicators we can possibly optimize, the efficiencies to be ensured? All of these aspects can have different directions. Some we increase, some we reduce, some we increase according to efficiency considerations. In this polar radar chart, I try to show you scenario by scenario. So each one of the scenarios are different wedges. If we normalize some of these values, we can see which one of the scenarios can have different perspectives from these different dimensions. So just think each wedge is one scenario. In each one of the colored bars, they are representing some sort of this multidimensional aspect of that scenario. So in the first region, we have 10 regions. In the first region, we have a scenario that has favorable or increased values for the non-biomass renewables, but it's not the scenario that currently has the best water withdrawal for electricity. Could this be improved? Next region, 2 scenarios in category C2, which has the most favorable values for water withdrawal for electricity, but not always having the most favorable non-biomass renewables. This can be improved. In Europe, the scenario in C1 has the highest or most favorable non-biomass renewables, but not having the best value for the water withdrawal for electricity. This can be improved. Southern Asia scenario in C2 has the highest agricultural demand, not necessarily coupled with the fertilizer used for nitrogen, but it's in C2. It's not in C1. Could this be represented in the C1 scenario? Latin America and Caribbean. One scenario that you see marked here, it has about middle, the electricity share and final energy. Could this be improved without necessarily overshooting or increasing the electrical energy storage that much? So this could be another way of looking at these scenarios. Middle East, the scenario in C2 has most favorable values for the water withdrawal for electricity, non-biomass renewables and primary energy, but some more synergies could be captured to bring such scenarios into C1 more. For example, you see this scenario in C5, which is not the temperature outcome that we really should be aiming for. We can do much better, but currently the electrical energy storage looks favorable, but it's not because there are high shares of renewable. On the contrary, this scenario needs higher shares of renewable energy. North America, a category in C2, which has the most favorable value for land use afforestation, but can this be improved? In another scenario for C1. Asia Pacific developed, we see the electrical share in final energy. It's about similar to some of the other scenarios, but could this scenario also be improved for different outcomes in addition to C3? So region by region, we can see some of the possibilities for additional improvement in our modeling as well as scenarios. Another scenario, the renewable energy share and primary energy, similar to some of these other scenarios that you see here on the top, but could we capture more synergies across these different dimensions? Last region, region 10, we see a scenario with high percentage of non-biomass renewables, so it is looking more favorable in our radar charts, but could we improve some of the other indicators? So you see here how scenarios are multidimensional, and as you're represented here, this is why it takes a multidisciplinary effort to enhance and advance our modeling capabilities. In looking to the next assessment cycle, there are priorities for models and scenarios interacting with the next coupled model intercomparison project. These priorities can be categorized into 5 areas: ensuring cross-sectoral integration and modeling, utilizing more granular inputs across systems, being explicit on the urban share emissions, better linking scenarios with various co-benefits, and ensuring comparability with the Earth's system boundaries. In the first priority, ensuring cross-sectoral integration and modeling, this is something that the LOCOMOTION project does very well. It has major advancements in this priority. This is coming from a recent publication by the LOCOMOTION team, from Professor Dewitt's research team. And in this table, you can see the different models, their coverage, their approach, their resolution, and you'll possibly see this table again. But the models that are looking at the hourly resolution, they're fairly limited, especially when compared to the integrated assessment models, because these are looking at annual or even 5-10 year resolutions. So better representation of smart energy systems in these integrated assessment models would require the hourly resolution of modeling. So this achievement from the LOCOMOTION team found a way to have the hourly resolution represented in integrated assessment models. So this is a very important advance that you will be hearing in the other models of the summer school. Second priority, utilizing more granular inputs across systems. These granular inputs can relate to land, water, socio-ecological systems. Here we see an example from land use efficiency. Land use efficiency has different values across regions, across urban areas. And here in the pie charts, you see the regional differences. Then in the green and red dots on that map, the green ones are the areas with improvements in land use efficiency over time, but the red ones is where it's worsening. So by using these more granular inputs, the applicability of the scenarios can also improve. Land use efficiency is also important for the transport mitigation, because having cities more walkable can also mean you don't need more vehicles. So this is the transport demand has very good synergies with land use efficiency, but currently the avoid, shift, and improve strategies in the assessment report, they're coming mostly from bottom-up literature, because integrated assessment models, they're not sufficiently including these aspects to the required level. So the bottom-up studies are feeding this area. Third priority, being explicit on the urban share emissions. For the first time in an IPCC report, the urban share emissions in the global total were reported. And this was a major advance because in the previous reports, this did not take place. So for different scenarios, here we see SSP1 1.9, which means 1.9 radiated forcing level at the end, 1.9 watt per meter squared radiated forcing level at the end of the century. So this is showing what it would look like for urban emissions with resource efficient and relatively more compact urban form versus moderate action. And this was also discussed in the scenarios forum this year, that this should be a standard in IPCC reports to include the urban share emissions and possibly designing the CMIP exercises to also report on the urban share emissions in the scenarios. So here in this graph, according to different existing models and scenarios, coming from image, message, and different the modeling community, these are showing what would be the urban shares in those scenarios. And the changes between 2020 and 2030, you can see here, it would require about 9.8 gigatons CO2 equivalent reductions for the scenario by 2030 from the urban emissions. We also looked into how the cumulative urban emissions compare with the regional share in the cumulative urban emissions. So region by region, scenario by scenario, these are showing the results. The year of net zero is also different for some of the regions, but it differs by the scenario, of course. So these are the advances. And another one, the range of the urban share versus the rural share of emissions. This is another advance that took place in this assessment cycle. So these could be continued, and there needs to be more systematic perspectives of how to be explicit on the urban share of emissions. Fourth priority, better linking scenarios with various co-benefits. We know the central role of Sustainable Development Goals for the sustainability transformations. Sustainability development goals, they're for the year 2030, but in the models, we need models that go to 2040, 2050, and then all the way to the end of the century. So what was done here, the target value, starting from the reference year, what would the value be in 2030, what would it be in 2050, and the same pathway for sustainability transformation. For example, the ending water scarcity normative goal, it would require about no increase in the water stress. So these are some of the aspects. And for example, the phosphorus flows from freshwater systems into the oceans. This would also need to be limited for 2030 and 2050. Another aspect of co-benefits is the employment. This figure on the right is coming from some of the employment co-benefits of integrated assessment modeling, and the one on the on the left is coming from integrated assessment models, and the figure on the right is coming from energy models. So this one, with about 100% renewable energy scenario, it showed about 134 million total jobs in power, heat, transport, and desalinization in 2050. We need more representation of such co-benefits in integrated assessment models. Also, zooming down to local level, we need to be able to show that these co-benefits exist for the communities, exist for the regions, and exist for the world. So this is coming from a recent example, again, on the co-benefits for the Delhi region in India, showing about more than 4.4 million employment benefits for 2050. And there are interactions among sustainable development goals. Some of these interactions, they are implemented, but others, they are either planned or conceivable to be implemented in the integrated assessment models. For example, good health and well-being, no poverty, good health and well-being resource use in this matrix, and life below water, and also the climate action. So these modeling. Recently emerging is comparing different indicators for sustainable development across different pathways, including for green recovery, but it's still emerging, and there is still a way, so we need more research into showing the SDG benefits of 100% renewable energy scenarios, which is currently a knowledge gap in the literature. Fifth priority, comparability with the Earth system boundaries. Can we vet models, can we vet scenarios according to how they meet the planetary or Earth system boundaries or not? By Earth system boundaries, in addition to a per capita, for example, level across the world, it is looking at how the Earth system really interacts at the local level. For example, how the water Earth system boundary interacts with land, with biodiversity, and nutrients, because nutrient overload is harming the water quality. So these are all integrated. For blue water, the most recent value in the literature says we need much less than 20% alteration of monthly surface water flows for all rivers globally. And there are other values, updated values for nitrogen, phosphorus, for example. So here you see the figure of the planetary boundaries. There are geochemical flows, climate change, land system change, but previously we had only looked at blue water. A new Earth system boundary has been defined for green water, for the soil moisture, for the evaporation, precipitation, and the Earth Commission is working on this. The Earth Commission says we also need a Earth system boundary for green water. And here you can see some maps from hydrological modeling at different levels. And the top two maps are showing the blue water, and the bottom two graphs are showing the green water. And the coloring is based on where this was transgressed from year to year. So already for green water, a majority of the world has already transgressed this Earth system boundary from many, many years. So we need comparability with these Earth system boundaries to be able to say this scenario meets the Earth system boundaries, this scenario does not meet the Earth system boundaries. And the stabilizing feedbacks, for example, how soil moisture affects the tropical forests, how that feedback, because we need to maintain about 80% of our rainforest, our Amazon rainforest, not to overshoot the tipping point, and we're at 81, so it's very critical there. But there are decreases in stabilizing feedbacks, while there are increases in amplifying feedbacks. For example, permafrost, global warming, and these are always changing. So we need to be more dynamic in how we look into the Earth system boundaries. So the first priority, when we compare with the within limits integrated assessment model, as far as I could access, the first priority directly is addressed by the 100% renewable energy system modeling capability, linked modeling capability with the integrated assessment model. Second priority can be linked to many different models, but for example, also including this environmental module, including land use. The fourth priority, it directly links with sustainable development goals, and as I learn more, also with the Earth system boundaries, the planetary boundaries. And the fifth priority, because it's looking into the tipping points, is very important that all of these aspects are represented in the same integrated assessment model. For the third priority, on being explicit on urban share of emissions, I would like to provide you a little bit more detail. The reason that we need to think about urban systems within the Earth system is because urban systems are important leverage points for some of the mitigation efforts that we would like to see in the world. So how they are planned, their land area, it has major difference across scenarios. The urban area, the urbanization has great impacts on resource use, integrating sectors, and how the urban planning comes together in an integrated way. It can really determine how our mitigation effort takes shape. So in my recent research, I looked into recent, published also, the urban emissions and land use efficiency scenarios for about 420 urban areas across the world. And using different data inputs, seeing how these would compare across different SSP1, the green growth paradigm is related and represented. This required bringing together multiple data sets, also using the global human settlement layer, the global grid model of carbon footprints that looks into the consumption emissions, existing static consumption emissions for urban areas, and also the SSP1 urban population projections per urban cluster. The focus was on the 420 urban areas with the largest footprints, and the different SSP1 scenarios had 1.9, 2.6, and using the trends in a 100% renewable energy scenario, also defining an SSP1 renewable energy version. So here we see different results. I will not go into the details, you can ask me more, but this is showing the results for SSP1 1.9. It has different urban implications for urban compact form with more widespread electrification efficiency, with relatively higher electrification of end use, renewable energy deployment than the other alternatives. This would require electric mobility, large-scale heat pumps, renewable energy, as well as material efficiency for the energy and material efficiency component of such scenarios. The other one, SSP1 2.6, it requires, it embeds the same principles, but with slower progress. So only high electrification, high renewable energy deployment, and the mitigation solutions, they're implemented not as quickly, not as rapidly as SSP1 1.9 would require. And this one for SSP1, coupled with the 100% renewable energy scenario, it would require the highest electrification, also including flexibility, which is very greater mitigation efforts from urban areas for vehicle-to-grid, power-to-heat, smart energy systems as well. So each of these scenarios have different implications for the mitigation effort to urban areas. So scenario by scenario, urban area by urban area, and whether they act collectively for these scenarios will make a difference. Here I would just like to go into one region. This is our region that we're currently in, the Southern and Eastern Europe. Out of the 420 urban areas, 32 urban areas were located in this region. And here we see the dotted areas, each bar is representing the scenarios. They are scattered across this region, and they are responsible in 2020 about half a gigaton of CO2 equivalent emissions in a consumption-based perspective. But these would need to be reduced to various levels by 2040, by 2030, by 2040, and 2050. In the SSP 100% renewable energy scenario, the value of these urban areas are coming to about 0 megaton CO2 equivalent. If we look closer into the top 10 urban areas in this region, these are responsible for about 353 megaton CO2 equivalent. In the SSP 1.9, it would require this reduction. This scenario that misses the 1.5 degrees Celsius target, it involves much less. And the 100% renewable energy scenario would require about 400 megaton CO2 equivalent reductions of urban emissions for the 10 urban areas that you see here. We also need to be, in communicating our scenario results, we also need to be clear that such scenarios have benefits for energy, health, climate, and avoided climate impacts. For example, especially in those urban areas with more air quality issues, this co-benefits, the climate or the air quality co-benefits would be dominating some of the other co-benefits. But we also need to be clear how these are very valid for improving the lives of urban inhabitants across the world. And this can possibly accelerate some of the action that we need to see in the upcoming years. So the total estimated co-benefits for top 10 urban areas across all the regions that were involved in this study resulted to about 9.7 trillion USD. And you can see how these can be associated with the Sustainable Development Goals, and 3 of the co-benefits also supporting the SDG 11 on sustainable cities and communities. One more aspect I want to draw your attention. We set the priority for land use efficiency. I would like to show how this could be used. So we know the existing land use efficiencies of these different urban areas, but we do not know how these urban land use efficiencies will evolve into the future. So we also need scenarios that take this into account in a future perspective. So how do we define these improvements? It could be 5% improvements for whatever the value of land use efficiency is for that city. It could be 15% improvements. It could be more parametric. We could be looking at how the urban areas converges to the average land use efficiency value or converges to the best regional land use efficiency values across time. So these are all possible scenarios. I would like to show some graphs relating to if the urban areas their land use efficiency converge to the best possible values of their region. So here you see the distribution of different points in the scatter plot. In total, these urban areas are responsible for about 83,000 kilometers square of built-up area at present. Some of these urban areas, they have very similar urban emission levels, but very different land built-up areas. And you can just think of these two examples, Greater Tokyo area versus Los Angeles, which requires long transport distances. Other urban areas, they have similar built-up area on the horizontal, but different outcomes in the urban emissions. And this can relate to different development levels, for example. If we follow these points, in this best land use efficiency scenario, how these are moving, changing across time, it would require both improvements in urban emissions according to the SSP1 renewable energy scenario and improvements in land use efficiency to a more limited extent. So this is showing the value in 2040 now. And this scenario, compared to some of the other scenarios, it is improving in both dimensions. So some of the other scenarios are not having as much improvements in both of these dimensions. If we follow it further 10 more years to 2050, we will see how this double challenge of nearing net zero and having this more optimized result for land use efficiency can play out into the future. So it's really a double challenge, reducing urban or decoupling urban population growth from emissions and land use change. Ask yourselves, this is a best scenario, but wouldn't the urban land use change also involve some kind of penalty for the CO2 sequestration of those biomes? The answer is yes. So taking into account local biomes of each one of those urban areas, looking into the CO2 sequestration, average CO2 sequestration potential per year, we can see what the impact would be in the year 2050. So each one of those are calculated, and then in 2050, we see about 1 gigaton penalty for the reduced CO2 sequestration potential due to the land use change from urban areas. If we do a sensitivity analysis, for example, what if the urban areas came within plus or minus 10% of the urban emissions of these scenarios? You can follow the results. The 10% is a very small bar, a small range, window opportunity, but these urban areas could come to about zero CO2 emissions for limiting global warming to 1.5. But when this penalty is considered, it would actually reverse some of the progress unless there's more mitigation efforts in urban areas. For example, urban green and blue infrastructure, bringing more nature into the cities. So these are also relating to some of your research interests that I heard in the morning. I would like to start concluding now, emphasizing that sustainable development is multidimensional. From the example of either the scenarios, in addition to that, I would also like to emphasize this key message coming from an index of sustainable development of energy, water, and environment systems. This index, the STEBAS index, has different dimensions relating to energy, CO2 measures, renewable energy, water usage, environmental quality, CO2 emissions, urban planning and social welfare, as well as sustainability policy. And this index can be used to guide the cities, urban areas that are so important in our mitigation efforts for increasing the renewable energy penetration, integrating urban energy planning, and decoupling emissions from greater well-being. Some of these cities, they have more challenged status than others. This is showing one of the urban areas from Turkey where I come from. Istanbul has currently a challenged city status in the STEBAS index. But if we look at the different urban emission scenarios for this urban area, we can see that this room for improvement can be linked to these scenarios. So this is an important opportunity for the urban area. But even those that are not challenged but have a more pioneering status, they can also improve. They can pursue 100% renewable energy scenarios because the urban areas is where this realization will take place. They can lower their ecological footprint, they can improve the urban planning. So even those urban areas that have different challenge, solution seeking, or transitioning, pioneering, they can also improve and possibly learn together. You might be asking yourself, so what is the #1 city in the STEBAS index? It is Copenhagen. Maybe it's not surprising, but it has a more advanced integration of the urban system than some of the other cities. 120 urban areas have been benchmarked according to this index. It's also one of the urban areas that is selected in the EU mission for climate neutrality by 2030. In the existing climate plan, there is emphasis on carbon neutral district heating, energy system flexibility, and on the institutional governance aspect. It is also emphasized for the business models how the partnerships for flexible electricity use at large scale can be employed. So also think how these scenarios can be realized in practice. It will need these type of solutions. The 112 cities that are selected, it's expected that they improve the energy transition, they improve the resource utilization, and it's also emphasized that system flexibility options, which can be power to heat, it could be vehicle to grid, there are different options. It will allow reaching much higher shares of renewable energy, as you also heard from the presentation of Nicola, and it can broaden the decarbonization efforts of the European energy system. This is coming from, you will be learning more in the summer school, the flexibility index. This flexibility index is developed to show how the critical access electricity production reduces as the flexibility index increases. And when you ask yourselves how these scenarios can be realized in practice, a major part of that will also involve the mitigation efforts to allow the infrastructure of urban areas to support this kind of flexibility. So coming to the end, always ask yourselves, learn more, question more, how these models and scenarios can be improved, how the efficiencies can be improved, how the flexibility, demand side flexibility can be improved. Because your questioning, your asking, and your curiosity to learn more will determine these improvements in these modelings, more advanced models, to guide the entire world, whether it is entire regions, the entire world, or urban areas, to do better for sustainable development. So intensified climate change requires intensified action for net zero. These results, when used in practice, can make world of our difference for our common future. In a recent editorial from the previous SEVES conference in Dubrovnik, this is also showing some of the achievements of the LOCOMOTION project for supporting advances in 100% renewable energy systems. So always keep in mind, mitigating climate change requires an effective approach that involves integrated, coordinated, and synergetic action. As an overall comparison, there are multiple opportunities to advance these priorities, advance these knowledge gaps through the within limits integrated assessment model, especially when all the modules are also interacting in the scenarios. And new and improved representation of smarter energy systems is a major advance in this model, the William model. So I hope that you will enjoy all of the modules, the resource, economic, energy, environmental, social, and demographic modules in the summer school, for including today, the next 2 weeks. So thank you very much.
Thank you, Shir. We have some time for discussion. I would like to go back to a question very important to us. When these assessment reports come out, we see a lot of technologies that we don't see in reality happening, like carbon capture and storage, nuclear energy. This is future according to EMs that calculate the future. But in reality, we see lots of renewables. The problem we see is because the way renewables are calculated is quite conservative in EMs. One problem is that they use a yearly step, while for renewables, variable renewables, one needs to calculate hourly step. They don't calculate or take into account flexible technologies. And this is something which we are trying to solve in William. It's very complicated. How was the discussion going on this? I would say one of the major critiques of EMs, which IPCC is using as a reference?
Yes. The assessment reports, they involve an extended reviewer community as well. So this is a major review comment that we had also received from the entire research community. And maybe it also helped us to develop the multidimensional feasibility. Because there, when we're looking into technological maturity, that also gives us a sense that renewables are technologically mature, carbon capture and storage is not technologically mature. Even if we're thinking in the power sector, it's not there yet. It's mostly coming from different applications, not in the power sector. So when that scenario, so some in their modeling capabilities, they are limited to looking into carbon capture and storage in a more limited way. But that multidimensional feasibility assessment will say this scenario has very large shares of carbon capture and storage. It has very large concerns for technological maturity because it's not there. So in that comparison, it will be possible to see that a scenario, for example, the illustrated mitigation pathway for renewables, which does have higher renewable energy share, technological concerns are much lower that you saw. It's not technology, it's the institutional barriers are high for that scenario. So that multidimensional feasibility, yes, we need to accept that different scenarios, different modeling capabilities lead to different results. But that layer of analyzing the feasibility of scenarios and of scenarios that are coming from different models, multidimensional will show us some of these different aspects. Also for nuclear, it has very high costs, very high investment costs, waste problems, and even public acceptance problems. So that institutional, technological, ecological, environmental is also a different dimension. That will also show in that multidimensional feasibility assessment, whether it's at the scenario level, and we also did another one at the mitigation option level. So we see that more feasible mitigation options would relate to renewables, also involving urban planning, because if we reduce the energy demand, maybe we don't need another power plant. So the feasibility, the co-benefits, the sustainable development assessment of the mitigation options, they're higher for what is more acceptable, more accessible. There's solar, wind all around us, why not use it? Technology is there, economics are very, very favorable. Another figure in summary for policymakers looks into what are the mitigation options leading to 2030, and you will see solar at the top. So all of these are considerations, but we as a modeling community, we need to be providing different scenarios, different options, so we can compare these results. We can show that, look, this is the 100% renewable energy scenario, and these are the others. And this is how it fares out in the multidimensional feasibility assessments.
More questions? Yes?
Okay. First, thank you for this presentation. It was really packed with information. We just wanted to ask if you're willing to share the slides.
Of course,
also,
of course. Yes.
And also thank you generally for the work in the IPCC. And I think IPCC really did humanity a huge service by integrating demand management this time for the first time. And just two small questions. You were showing negative emissions in the urban context, and I was wondering where did this come from?
Yes, that's a very good question. So different models, for example, the image model or some of the others, they are involving some different results. But also the carbon dioxide removal, it does also include land use afforestation. It's one of the options for carbon dioxide removal, CDR. So it's not necessarily coming from CCS, which is the storage part of carbon dioxide removal, but the most sustainable carbon dioxide removal is land use afforestation. But now, when we think about the feedbacks, there's more wildfires. So how that urban, so we can't rely actually on land use afforestation because it involves very much uncertainty. Will that forest be there in the future or not? So we need to reduce emissions as much as possible, and when new scenarios come out, urban emissions shares in those scenarios would be different. So those were the urban shares in existing models with different values, also involving the land use afforestation. For example, an urban area can say, this is my urban planning, I set this carbon sink and enhance the carbon sinks. So there are different ways these can play out, but in the end, we need to be thinking about reducing emissions more rapidly, increasing the renewable energy share. These are more sustainable when we think about the mitigation efforts necessary.
Luis had a question also.
Luis,
you have a second one, but he has a second one.
Yeah, but
Let's have a priority.
Yeah.
okay, then quickly, when you talk about decoupling, you talk about 27 countries and
24.
24, sorry, yes. Do you remember the time period? And was it
Yes.
consumption-based or production-based?
Yes, so these 24 countries, both territorial emissions and consumption-based, they had sustained reductions in CO2 and greenhouse gas emissions. They do involve North Macedonia, Natasha, it includes North Macedonia, and some other countries, also Jamaica. You might be surprised, but so different countries around the world. It is some of the countries, multiple coming from Europe, but we do see examples also from other regions. Our models need to be showing us how these number of countries can be increased more. So there's no, 24 is very small, just a handful of countries, I would say. We need, those models need to be showing us so those countries can put their development pathways into a more sustainable, so communicating results of scenarios is very important. Developing models, advancing models on development side is one aspect. Communicating policies, or European Unicom, the Green Deal is based on an SSP1 type of scenario. So we need to increase this more. We see as the best practice from the model results.
I have a question directly related to that, like regarding the decoupling. But is it like when you mentioned it's many European countries, and I said like Germany
Yes.
In my mind.
Yes.
So we had fairly high emissions in the 1990s and also through the 90s in general. And we reduced a lot of these emissions in general in Germany. But I think a lot is also done because we outsourced many of our polluting industries. So I think this image can be, I don't know the base of the calculations of these graphs, but I think it can be misleading because we can see like the same consumption pattern in most of these countries, or even rising consumption patterns because we have rising GDP and we consume more products. But the emission is produced in other countries.
So that would be very important to see how the territorial emissions compare to the consumption base. The number is less, so 24 is relating to reductions either way, but in the summary for policymakers, it's exactly 18 countries that have sustained territorial and consumption-based CO2 reductions in these decades. So that would answer your question that there are 18 countries, at least, it says at least 18 countries that have sustained reductions across decades for territorial and consumption-based emissions. We can say for cities, some cities, they are increasing their consumption-based emissions, so it was important for us to look from the consumption-based perspective, because a lot of consumption takes place in cities, but there is signs of progress that is also emphasized in our report, that there are reductions in both territorial and consumption-based.
Data is available
Yes.
on our world in number, in data. So you can say for which countries it's different,
Yes.
but for most countries, it's actually relatively small influence of outsourcing production. I was surprised by that. But it's only a few percent for most countries. Some countries have completely different numbers with, if you take into account consumption emissions. But check the data online. Luis?
Yes, well, I think, well, related to this point, I'm not sure how you manage the data, because it's not so easy to take into account the consumption with all the trade data and so on. And I have read different reports with different results about that. So just a small doubt about the uncertainty of data, but my question was different. Well, first of all, thank you very much for the presentation and all the ideas, suggestions about the William model and so on. It is very, very useful for us, of course. But the second, yes, specifically about you mentioned the relevance of the city emissions, all the city's emissions. And well, in our model, as you know, we have no this kind of desegregation of city level for geographical purpose. It's quite difficult because our geographical level is just a country, in the case of Europe, or region. So we are not able to disaggregate at a city level. However, we have a couple of, let's say, information that may be quite related with this kind of city emissions or something like that. It's about urban places. I mean, because at least in the case of Europe, we will be able to have segregated information about the urban population and rural population. So, as far as I understand, most of the, let's say, urban emissions you mentioned are related with the people that live in urban areas. So, I guess most of the information about urban we can obtain from the consumption of people living in urban areas. Indeed,
Yes.
this is a question.
Yes.
So from this point of view, at least for Europe, we will be able to have this information in a segregated way. So emissions due to urban areas and emissions due to rural areas. We don't have at the moment this information for the rest of the regions outside Europe because it's not so easy to get this information and to include. And this is one point, and the other point we have also is just about all the different land uses. We have a specific use for urban, of course. But just a question. Imagine, as hypothesis, that we will be able to change the mainstream in the way that most of people is going from rural areas to urban areas at the moment. So the urban population is increasing and rural population is decreasing in most of the countries, I think. Imagine we are able to invert this tendency. So people go to the rural areas instead to go to the urban. Do you think that the change will think in the results?
Yes.
I mean, it's because the real question is, the problem is that urban areas by themselves are much more CO2 emitters, or the problem is that the people that are living in urban areas are higher consumers than the people living in rural areas. This is
a very important question. It's also one of the questions that we try to address. But our data, the analysis, we had data on urban carbon footprints for about 13,000 cities around the world. And using this data, not for the future, but what has been realized, when we look into this data, the urban per capita emissions is lower than rural per capita emissions in most of the regions. So this perception that urban emissions per capita is higher, it's actually not. It is lower because of the efficiency gains of on a per capita basis. Yes, there can be more people living in that urban area, but on a per capita basis, compared to rural areas, the emissions can be lower. Where do we see it the other way around, that urban emissions are higher than the rural areas? It's in Asia. And this is possibly a concern because the urban population is expected to increase in Asia. And if a person living in Asia, they move to the city, they will have a relatively higher urban per capita footprint compared to the rural inhabitants. But this is, we answer this question, we say in most regions, urban emissions per capita are lower than rural per capita, but it depends. It depends on many factors. It includes urban form, consumption patterns, energy infrastructure, and lifestyles, income. So it's very, very different. But at least this analysis, this new analysis showed how urban per capita emissions can be lower in most of the regions, but there are exceptions for some.
Yeah.
If there's enough time.
Well, we are already 5 minutes after, but we can.
Yeah, we can continue.
We'll stay
My
here
favorite
as
question.
long as you have
My
questions.
favorite question. Renewables. Some people say, well, there's no material for renewables. And the question is it possible to decrease, and what are other opportunities to decrease CO2 emission other than renewables? Because you say it's important that we touch upon renewables are in representation during the locomotion, and that will allow more people to understand the importance of it.
Yes. So, as the social awareness, especially that renewables are lowest cost mitigation option that we have in addition to some lifestyle changes. But for example, solar energy, wind energy, electrification of different end uses, lifestyle changes, all of this that I just mentioned, they have values that are below the reference system that they replace. So what are they replacing? They're replacing the fossil fuels. So this is an important aspect to communicate the awareness. It will also improve the multidimensional feasibility, because as there's more public acceptance of renewables, then some of the possible barriers that can stay in the way can be addressed. But public awareness would be important to further, so we need to use enablers. What are the enablers? They are the co-benefits. When a renewable energy system comes into your neighborhood or comes into your energy system, it improves air quality. If people are made aware of this, it is going to improve my health, it's going to improve my air quality. I can walk and run in the pedestrian streets or in the forest without having to think about this air pollution. So this perspective of co-benefits is an enabler, and policy making needs to use this enabler to overcome some of the barriers if they exist. There are many, it depends on the context, so these are context specific, but awareness building is one, material use and consumption is another. We cannot say, I'm 100% renewable, so I do nothing else. Yes, other things are important. Do you choose to locate close to where you work, or do you choose to live in a very distant area, because that will impact your transportation. Even if you're using an electrical vehicle, that transportation distance will have some kind of energy use. The energy use could be used in more decarbonizing other parts of the system. So in addition to technologically going to the renewables, also some additional demand, void shift, improved type of strategies are important for integrated aspect, both on supply side, demand side, and how all of this comes together. Did I answer your question?
Yes. I'm happy with your presentation and answer.
Thank you. Julia.
Natasha, do you have a question?
Okay, yes. Thanks, Shir. Now we see that a lot of efforts have been made in order to connect mitigation scenarios with sustainable development goals and planetary boundaries and all these other things which somehow have this climate change mitigation integrated, but much broader than climate change mitigation. So my question is, what is the difference compared to assessment report 5? Did the science manage to make these connections stronger under the 6th assessment cycle?
Yes, in the 6th assessment cycle, a very dedicated theme running throughout the report was shifting pathways of development towards sustainability. For this, it required more assessment of literature in a systematic way, coming from the bottom-up studies as well, not only integrated assessment models, but from multiple lines of evidence, bringing how both the bottom-up studies and the scenarios showed how the co-benefits can be realized in, for example, pathways that involve renewables, because it will improve the health of people, provide employment opportunities, and seeing both. There are mostly synergies, there can be trade-offs, but also knowing these aspects can improve the decision-making, because there are alternatives. They can be improved, for example, when integrated or prevented, the policymaking is done that way. So it did improve. There were very detailed assessments included also in supplementary material of how different mitigation options were related to each one of the 17 Sustainable Development Goals. So in this sense, there was a big advance also, because when the AR5 it was adopted, then the Sustainable Development Goals came into effect. So our literature assessed from 2015 to the present levels, and there has been a massive increase in literature looking into how mitigation is coupled with synergies with Sustainable Development Goals when there are trade-offs. So all of these were assessed for the first time in our report because Sustainable Development Goals were new. And I would say that it also interacted with the multidimensional feasibility assessment, because when there's public understanding of the co-benefits, it can improve the enablers. So there are these type of novelties included in the sixth assessment report. Thank you.
Okay, so thank you very much for having this presentation, and I would like just maybe to raise one comment and then a question. So we often talk about changing behavior, which is necessary, but maybe following up on Julia's question, there is one interesting for me information, that is that 90% of the maritime transport is transport of goods, so in the global market, and this transport, so 90%. That means, for example, travel is 10%. Of this percent, around 40% falls to transport of fossil fuels of some kind across the oceans. So many ships, 3 times more. That means 40% of the time. 3 times more than we travel, we transport around fossil fuels. Also helping, additionally, the climate change, helping acidification of various regions of ocean. So this, for me, somehow underlines the necessity and urgency of transition in power sector first, and then also supporting innovation, supporting technologies that help us fully exploit the production of electricity from sources which we don't need the fuel for, which we do not need constant travel of this very, very large number of ships. Also, we know at least a couple of examples of disasters in the sea because of this kind of does the IPCC report also reflect this particular issue?
Thank you very much for that comment. Of course, the shipping emissions are included, and part of that shipping would include the transport of fossil fuels. So that footprint is there. And especially if it's a consumption-based, I would say that they are included, but their shipping is not included in the urban consumption-based emissions. So it's excluding aviation, shipping, and some biogenic source of emissions. So this is the definition in the summary for policymakers. But in the detailed assessment, of course, shipping emissions have also been assessed. And you can see it in the graphs. It will show what is the aviation, the shipping, and different aspects also in transport. So not only the land vehicle transport, but the shipping transport emissions are also there. I would again refer to the multidimensional feasibility assessment. So for example, one of them also included phasing out fossil fuels. How does it fare? Yes, there can be some institutional barriers, possibly, mostly, probably. But the environmental ecological impacts, when we phase out fossil fuels, then this transport of fossil fuels across the oceans will not lead to oil spills. It will not affect the water quality. It will not affect biodiversity living in the oceans, the whales, the dolphins, every living being. So from an ecological and environmental perspective of that mitigation option, phasing out fossil fuels, its literature has a strong base. We can look from supplementary material, but I would say it would be one of the environmental ecological enablers for this option. When we phase out fossil fuels, there will be numerous, not only climate, but different planetary boundaries that will be associated with avoiding some of the waste that can lead in oil spills. And other mitigation options, they have different waste problems leading to health problems and so forth. So it would come across of the environmental ecological assessment. It can either be enabler for some, it can be a barrier for others, but the literature is assessed according to this type of systematic view.
Yes?
Yes, thank you so much for the presentation. I have like 3 questions.
Three, what's one?
First one, I was wondering if there is any scenario that Introline just it's based on existing technologies and not based on expected speculative ones, like negative emission technology or this kind of, like if there is a base one.
So in the 3,000 scenarios, and then when they're vetted against the criteria, we had about a little bit more than 1,500 scenarios included. There are many, many scenarios, but for example, no negative emissions, it would require 100% renewable energy. So in a very fast time, in a very rapid time. So if we also delay the 100% renewable energy pathways, then again, we still will end up, how do we fit in the missing reduction? So it would require more 100% renewable energy scenarios with the integrated assessment models. So I would see that.
And now?
And now, yes.
Yeah, because we are at 1.5. But if we don't want to reach 1.5, if you are okay with 3 degrees, I think there are a lot of scenarios without advanced technologies.
It depends on temperature.
RCP 4.5, 6.
So that's currently where we're headed right now.
Yeah.
So
exactly. So this is business as usual.
Business as usual.
Okay. The second question would be about if there is any scenario or if there are part of the assessment that takes into account the national historical responsibilities of nations, like the different responsibility that have the global north, global south in terms of climate breakdown.
Yes, so the cumulative emissions, they're also reported from previous decades, how it plays out in the regional sense. And different scenarios would involve, for example, higher reductions in some regions. That could be different, but again, it changes from scenarios to scenario. But I think it would be more important now also to say what is the reductions and how it compares to the cumulative. But we have come to such a point that if we don't allow reductions in every region across the world, it's not possible anymore. We cannot say you reduced or you consumed this much emissions, you reduce very quickly, and you continue to increase. That's not possible in a 1.5 scenario. In a 1.5 scenario, all regions now need to reduce. There's no exception to that. So how much you can account for cumulative urban emissions, we already crossed, or cumulative emissions, we already crossed the point. So all regions from this point onward need to decrease for 1.5, for 2, for different temperature outcomes. There can be some faster reductions in some regions, slower, more gradual peaks, but not time to peak for 1.5 was for all regions was already previous. So we need to.
In a way, this historic responsibility has been recognized by Kyoto Protocol, in which only Annex 1 countries were supposed to decrease emissions and develop technologies which are necessary for everyone to even decreasing emissions. But with the Paris Agreement, which started in 2020, everybody is now responsible. Because if we continue with this argument of historic responsibility, we are not going to save the climate. There is no way. Because the historic responsibility is a small one compared to the current dynamics. So we have done that. And I think this was done in a fair way, because these 20 years between Kyoto and Paris, we have invented technologies. So these technologies are not any more expensive. They're cheaper than fossil fuel technologies for the poor countries. So I think it's fair that we can say that everybody should decrease emissions. Of course, we don't expect African countries to decrease emissions because they have no emissions. But we do expect that China and India start decreasing emissions, because for them it makes completely economic sense. It's cheaper to invest in solar and wind energy in China and India today. So this is not affecting their ability to grow, which is important. I agree they have to come to our level of development. So their work on the litigation is fair now. I don't know if you agree with me. No, you would still like to polish the bed.
Absolutely.
A little bit.
The last question, I want to ask if we are, or how far we are in adding some post-growth mitigation scenarios in the report of the IPCC?
So post-growth, it comes from, you would see this more in the building chapter. The building chapter, they had this sufficiency, efficiency, and renewable framework. So more sufficient type of floor use, efficient technologies, and also the renewables. So all of that was considered. But post-growth, we discussed about this. For developed countries, it makes sense to reverse development paths. But when we try to communicate post-growth to, for example, developing countries, it may not resonate as much because the impacts that we're trying to reverse is targeted more for the countries that have already surpassed some level of consumption of emissions. But I think the avoid, shift, and improve strategies are very important for that. So instead of thinking about, for example, using your vehicle, there are other active modes of transport. For example, walking, cycling, that also has co-benefits for your health. How close we are. So the multiple lines of evidence are mostly coming from the bottom-up strategy, bottom-up literature. So this could be represented more. As I mentioned, I showed the indicators in the AR6 scenario database, what we know about some of these indicators that are important for avoid, shift, and improve strategies. They're not as much that you saw in the presentation. So we're close, but possibly not close enough. But I would emphasize that it will actually be a combination of green growth and reducing demand. We cannot rely only on reducing demand. We need the green growth. Green growth in the sense that we decouple emissions from greater welfare. This is also actually, maybe the disciplines are currently not integrated enough. From my perspective, I see these two, green growth and post-growth, they can be integrated. How? We reduce demand to a certain extent, we increase renewables, and these two can be our sustainable development. Like we saw in the illustrated mitigation pathway for sustainable development, what did it do? It integrated reducing the demand with renewable energy. If you think about it, it's integrating the green growth with the post-growth. And I see this very promising.
Yeah, that is exactly what post-growth is saying. So post-growth would never say we should not grow renewables. So it's not integrating, it's just the baseline post-growth.
Yes.
Yeah.
We have a definition. It's living within the planetary boundaries, also in the summary for policymakers. But from what I sense, I listened a lot to this type of discussion. So from my view, at least, I wanted to share this.
No, yeah, I have a question for a comment. I don't know if it's a question or a comment related to this and also to the coupling and green growth and all of this stuff. That we are considering GDP growth, which might be boosted by the financial system right now, and we are creating this wealth which is not real, and this might be also increasing the GDP artificially without the real economy sustaining it, and debt and all these problems. So this decoupling might be also like fake in a way, and green growth, like, I don't know.
We can have alternative indicators to GDP. For example, Human Development Index is one possibility. There can be even more. So we should not only rely on one indicator to look at. We could look into population. We could compare population growth with emissions without using GDP at all. This could be another way of looking at decoupling. So it's open to discussion, I would say. One thing I wanted to return to your third question. When we say we need a safe and just corridor for the planetary boundaries, the Earth system boundaries, that's actually looking, so not only climate, we already transgressed, or if when we continue in the same path for several more decades, we would already be transgressing. So we need system transformations to bring humanity back into safe and just corridor. But for example, I would say it's more promising to look, for example, it's a water scarce city in a still having some needs for basic sanitation, then that city, for example, should be having a greater priority for coming into the safe and just corridor. So your question, if we look not only for climate, but we also look for water, for nutrients, for water security, we can also translate your thinking into the safe and just corridor for the other planetary boundary domains. But for climate, it's very critical because it's interacting with all of the others that we realize reductions.
If I could give a comment on this fake GDP growth. So look at cars. In rush hour time, 25% of cars are on the road. So why do we buy so many cars? Because cars used to be a kind of man symbol to get women laid. It's not anymore so, because now we have Tinder, we have social networks, and young men get laid in other ways. So we have new economy of Tinder, of social networks, which solves the problem why initially we had too many cars. So we don't need these cars, but this is not the fake growth, because the final reason why people were actually doing this activity, or at least the male part of it, is to get laid. They don't need it for transport, but they needed it for some other purpose. So I don't think it's a fake economy, it's a new economy. We are moving away from material economy towards the value economy. In the end, we are still satisfying the same type of needs. We need to eat, we like to socialize, we need to live somewhere, but we can do it with much less material. But it may be more expensive, and then GDP can grow, but the materials we need for that GDP can go down. So this is the idea of decoupling. Less material, more value.
I would say that the moving the economy to this service economy from the product economy is going to be difficult, and also get people to pay more for the service than they get from the ownership is going to be, in my head it doesn't work really, because it is cheaper to own the car because it generates less GDP than
young people
having
are
the service.
They're not buying cars anymore.
Because they use them.
No, it's cheap to buy a car. You can buy a second-hand car or with low installments.
Yeah, of course. I mean, it's cheap to buy a car, but it's not cheap to operate it.
Okay, yeah.
You have to pay insurance,
You
you have
don't
to pay the
really
fuel.
need a car anymore to get from point A to point
That's
B.
true, that's true, that's true.
And you don't need it to impress girls, because girls don't get impressed with that.
But I would argue against that we use less material consumption. If you look at your personal home, how often used to people refurnish their home? Now people go to IKEA, they buy like a kitchen, they buy like furniture, they use it for 5 years, then they're bored of it. They throw it out, they buy new shit. Phones get replaced on a yearly basis.
That's a fashion problem. Definitely, I agree with
I mean,
you.
it's a fashion problem.
It is
It's
not
like
a
when
We
we
have to
have
change this fashion.
Yeah, but it
Lots
doesn't
of
material
insecurity.
consumption on all levels. I mean, we have like the laptop. You will replace it in 2 years. Before you would have bought a laptop or like a computer, it was 3,000 German Deutschmark to buy one computer. You would like be super fucking careful with it. You would make sure that nothing happens to it, and you would definitely not throw it out very quickly. The same with the mobile phone or like with the telephone. You will replace clothes like it would be nothing. Like, oh, today I feel like I buy new stuff. I mean, we do this on all levels of consumption. So I think it's a myth that we tell us that we use less materials. This is an absolute lie.
Because the problem of owning economy. If you go to service economy, then you just pay for what you actually need.
Yeah, but this is very dangerous as well, in my opinion, because when we go to a service economy, like this kind of service-based economy, then we end up with subscription models of all these kind of like this new trend of subscription models, which is in the end it is a form of slavery, because you're just like always paying, and you have less and less of your own capital for your own decision making, because you're like obtaining the service, you're obtaining the service here, and everybody tells you that you need a monthly or yearly subscription, you get less and less capital, you have less and less freedom of choice to do what you want with all of that. I think that's very dangerous. This is
Okay, but this is a different subject. That's maybe freedom. Did you want to comment on this issue or another? Because I have another question there waiting.
On this, but why is there so much time?
On this? Is it on this?
On Laura's initial
Laura's,
point, which was, like, I think much more important than lifestyle changes, was your point that a lot of GDP growth is income from financial assets, which is not real. And that means that a lot of the decoupling in many countries could be due to the fact that the actual material wealth of most people is decreasing, and thereby also emissions, whereas the income of the richest 1% is increasing so much, and this is counted in GDP, which means that we don't have decoupling, we just have recessions that are hidden. So this is how I understood your original point about the fake wealth, and that has nothing to do with cars or Tinder or anything else. Maybe I misunderstood.
I remember a paper that I read, but I cannot tell like 100% that the GDP is in a way growing because of the financial system and not because of like people owning cars or, well, of course, when you own a car, you might be in debt for some time, but all this amount of money that is
Money is not what destroys nature, it's the materials that we use. So we actually want to reduce the amount of materials that people use. We don't want to reduce necessarily their comfort, but why to use more materials than we need for their good life? So the materials should not be a measure of wealth, although it used to be. But money is actually a better measure of wealth, because if you have money, you can buy something which is maybe not so material, or at least you can be safe in the future.
Not well-being. Sorry, not a measure for well-being.
like people are paying
Money. Well, I would agree with that for sure, but the question is, how are we going to measure well-being in a better way? You know, GDP is wrong, we know it, but it's the only measure that it's relatively easy to measure. Everything else is complicated.
One point that I want to add on this resource issue, for example, we were talking about consumption. A lot of the consumption also relates to the consumption of materials, not only for personal day-to-day use, but how we build the cities. And if we look from that macro level a little bit more, we will see that lightweighting, yes, you need to have a secure built infrastructure, but lightweighting of materials, for example, can you, instead of steel, can you use something with the same strength that's also less energy intensive? So lightweighting of infrastructure can be another way of reducing resource demand. Then material recycling, yes, maybe there are some limits to how much you can recycle, but enhancing practices for that. Also ways of coupling infrastructure with people choices. Because one way, if you don't have the infrastructure there, then do you have the option of recycling that much? Or if you don't have any public transport, do you have the option of something else, not to, an alternative to using your private car? So we need not only people choices, we need choice architectures that are coupled to the infrastructure availabilities. And if you integrate that in an urban perspective, ways of finding lightweighting to reduce the material resource use would be also very important.
We have a question there, please.
Yeah. Okay, so building on from some of the things that came on, I think in IPCC third group report there is an amazing chapter, chapter 5 on demand, yes. And so on that in fact answers that question on how do we measure well-being and so on, that has nothing to do with monetary terms, and that builds on the theory of human needs and so on, and sufficiency and post-growth. In fact, I think that's a chapter of post-growth, but it's surprising that having that amazing chapter, then the scenarios analysis is not having that that perspective on sufficiency that much. And there was an interview published in the Rosa Luxemburg Stiftung to Jamina Saheb and Kai Kun-hen, that they were talking there that there in the recent years there has been some research from Julia Steinberger and Kai Kuhnhen also, that they built different scenarios, bottom-up scenarios and so on, but that they were not able to send those scenarios to the dataset of IPCC because of the complexity of that dataset, and they are a small research group that are not able to manage to translate their research. They attempted the small research into those scenarios. So, do you think it is possible that this small research group are going to be able at some moment to push their scenarios and the results into IPCC? Is there something that can be done in the way that to encourage or to push that to combine that knowledge of chapter 5 with those scenarios that nowadays are not present?
So chapter 5 that you mentioned is also one of the novelties of AR6, because it's bringing more of the social sciences that I know that you're interested, but bringing the social science literature in a way that relates to demand, because reducing the demand from material resource use, it involves lifestyle changes, behavioral changes. So more social sciences is needed to understand how that could be increased. I would not say, so the AR6 database was open, and every research team had equal, yes, there are very large consortiums, and they have maybe more direct access, but it is the vision that the Working Group 3 database received scenarios from whatever research group. Some scenarios, they reported whatever indicators they had, so it's not a limiting factor that some scenarios report less indicators. But at least from the viewpoint of IPCC, that database was open to all research teams. So in that aspect, I would like to say that the IPCC did open this database to all of the research community. They're my colleagues, so I respect also their views. But at the same time, I would say that the demand chapter did a very good job in looking into the avoid, shift, and improve strategy. So the avoid also relates to urban planning, more compact urban form. Shift, improve also relating to technological improvements, shifting demands. So the demand chapter is a very important aspect, also relying more on the social science literature. As it stands right now, it is coming mostly from bottom-up studies.
Okay, I think we have exhausted questions.
We continue on the beach.
Yes, but before the beach, I would like to thank Sheer. Thank you very much. I have a question. Who's feeling too hot?
No one.
No one. Good. Okay, because climate resistance put this to 27 degrees. Okay. So, would like to say something more?
Yes, I enjoyed learning about each one of your research interests. There's a very good diversity, so use this opportunity of the summer school to enhance your multidimensional social sciences, green-blue infrastructure, energy-water nexus, ecological, environmental economics, industrial engineering. So use this opportunity, energy modeling, to interact and exchange ideas for supporting the future of sustainable development.
Thank you, Chair. Okay, so who wants to go with me to the beach? Okay, not too many. Then, yes? Oh, very well. Well, I will take you to the typical Croatian beach with its rocks.